Hey guys, welcome to the video. So I want to discuss a very something which is often overlooked, knowingly or unknowingly, in physics or in the practice of science, or even in general, even outside science, in the way we live our lives, maybe. So it's kind of both a science video, scientific video, as well as general, like a perspective kind of. So, and as you can understand from the title, it's about keeping things simple. Of course, science is, I mean, simple things are not interesting. And most of us do science, or even most of us, we want interest in life. I mean, we just don't, uh, we are here for, I don't know, like some few years, 75 years, 80 years. So we don't want to spend that life doing simple things. On the other hand, we want to understand simple things so that we can apply this knowledge to better understand complex things, which are hard to understand. And that challenge is what makes it interesting, right? And that's of course that's a very valid point, and I do not deny that. Interesting things are always important, right? In life, to give meaning to your life, maybe not intrinsic meaning, but it gives you something to live for, and you need a passion to work on. I'm not saying it has to be science, but it's usually something that is interesting to a large group of people, maybe not everyone, but to a large group of people. For instance, nobody will find 2 plus 2 equal to 4. Nobody will find this interesting until and unless they are a very young high school student or something, like in their early stage of their schooling. Otherwise, no one of my age or older than me will not find this interesting. Number one. Number two, this is one example. On the other hand, number two, the universe or Big Bang or maybe even consciousness. These things, maybe not every one of us study these things professionally, but 90% of the people, most of the people will find these things interesting, right? So that's the thing. But that's a valid point totally. But the point I want to make in this video is that in our pursuit of understanding complex things, or keeping things interesting or whatever, what we often do is we forget to keep things simple. Now we should not, I'm not saying that we should aim to understand simple things and stop there. Our aim, we should not keep our aim simple, or we should not keep our aim confined to just simple things. But when we're fall but we should follow an approach, the approach that we're following, the path that we're following to achieve our aims of understanding stuff. We should not make that path overly complicated from the beginning. That is the point of this video. I'm not, so be very careful. I'm not asking you to stop thinking about complex things and study only simple things. That's not what I'm doing. Sorry, yeah. So basically, the reason I'm telling this to you is that, for instance, let's start with a very simple example, which is velocity. So how do you think was velocity like defined? Like it's we all know what is velocity. It's in very simple terms, without going into the calculus derivatives and the exact difference between average velocity and the instantaneous velocity. Without going into all of that, in simple terms, for layman, the velocity is distance divided by time. Now, do you think this definition dropped from the sky? Of course not. We humans came up with it. Now, my question is, why could not we could have defined velocity as distance squared over time? Maybe. Even then, see, we understand that the faster, even qualitatively, without going into mathematics, even qualitatively, from very common sense, we understand that if something covers a distance in very short time, then it has a higher velocity. More the distance it covers, more its velocity. That's why it should be directly proportional to velocity, to distance, because higher the distance it covers, it has a higher velocity. But there is a correlation with time, because I can cover 100 kilometers, which is a huge distance, in 1 million years. So in that case, if people say that since I have covered 100 kilometers my velocity is high, that's not correct. Because you also have to mention in what time have I taken to cover 100 kilometers. So once you hear that I've taken a million years to cover 100 kilometers, you will just laugh at my velocity, or you are slower than, uh, I don't know, you're slower than everything. You can just do the maths and find out. In that case, my velocity in kilometers per hour would be 100 over 1 million. So how many zeros? That 10 to the power minus something. You can meet kilometers per hour. Now the point is, so even from common sense notion, we understood that to define velocity, we need velocity depends simultaneously depends both on the distance we are covering and the time we are taking. If someone says that I covered a distance in 1 second, you will not suddenly jump to the conclusion that I have a very high velocity. They have, whoever made this claim, they have a very high velocity, because they have not specified what distance they have covered. They have just said I have covered a distance in 1 second. Now if the distance is maybe say 0.1 meter, so covering 0.1 meter in 1 second is not a very high velocity, right? So these are the things we need to be So anyway, so there was a need, like there was an understanding even without going into calculus, mathematics and everything, instantaneous velocity, average velocity, or everything. There was this understanding that we need to refer to the concept of both distance and time simultaneously to define velocity. That's fine, number one. Number two, it was also understood that when both of these are taken into account, then more distance means more velocity. By that I mean you also take time into account. So for the same time, if body A covers more distance than body B, then object A or body A, it has a higher velocity because we're keeping the time fixed for both the bodies, right? Similarly, for the same distance, if body A takes more time, then it has less velocity because it's taking more time. So yeah, so then a very natural choice would be distance over time because it's directly proportional to distance. So more the distance, more the velocity, and it's inversely proportional to time. More the time, less the velocity. So velocity is distance over time. Now this is not a derivation, right? Velocity is not something we discovered just like there are stars in the universe other than sun. It's not a discovery like that. There is nothing called velocity. We invented this concept because it makes the study of moving objects easier. That's the only thing. It was not something which was waiting for us to discover we just made up this concept, and it's a very useful concept. But now let's come back to the question I made. If it was distance squared over time, what would have been the problem? I mean, distance squared over time, even then if the distance is more, then velocity is increasing, and it's also inversely related to time. Problem would be squared. Anyway, I cannot use squared because see, velocity is not speed. Velocity is direction, dependent on the direction. So if I move forward 10 meters and then come back 10 meters in the opposite direction, for retracing my path, initial path, of course my velocity would be zero because my net displacement would be zero. My speed will not be zero because I have covered this distance in some speed, right, forward or backward, but my velocity would be zero. But now if you define it to be distance squared, then you can understand this direction you're getting lost. This dependence on direction is getting lost because what opposite direction means, let's say minus 20, not 20, let's say we are moving in the plus x direction, 10 meters, so that's in like let's say 10 meters in plus x direction. Now if I come back 10 meters in the minus x direction, opposite direction, but my question is, if you square the distance, then whether it's minus or plus, it will always get squared and have a non-zero contribution, which is not what we want. But forget all of that. Let's say you make a distance cube over time. Now you don't have the problem of minus x cube is also, like the minus remains. If there is minus remains because you're cubing it. Now the question is, even then, if you define velocity to be minus or whatever, to minus distance cube over time, then also it's directly proportional to distance and inversely proportional to time. But it's not a linear relationship anymore. If your distance becomes a little more, your velocity increases to the cube, like exponentially. So this cannot be proven mathematically, intuitively. That's what I'm trying to say. Sometimes your logic, like you should, this is why I brought up the example of velocity, because you should keep things simple. So maybe in some cases it might appear that a distance cube over time works, but why will you complicate things if distance over time works just fine? Number one. Number two, it's not just a matter of simplicity and complexity. Even our real life experience, say something is moving at 10 meters per second and something else is moving at 20 meters per second. Forget it. We are trying to define velocity, so forget let's not use the word meters per second, because that means we have already defined velocity. Let's say object A covers 10 meters in 1 second, object B covers 20 meters in 1 second. Basically we're just fixing the time. So then, just by intuition, I mean without going to any mathematics, you feel like object B is twice as fast as object A. And if you define your speed or velocity to be distance over time, linear relation, then this actually holds. 20 by 1, because 20 meters by 1 second, distance by time, and this is 10 by 1, so 20 by 10, the ratio of their velocity is 2. So indeed it's twice as fast if your definition of velocity is distance over time. If it's distance cube over time or something else, then this no longer holds this. And this is not just an intuition, this is a correct intuition, because correct in the sense, again I told you, velocity is a concept we made up. It's not given to us, so maybe it's not correct as in it's a law of, not correct as in a universal law of nature, but at least I can say that it's a useful definition, because using this definition of velocity, I have defined a lot of other terms, other parameters in physics, and I have done classical physics using this, and I have been able, most importantly, I have been able to apply these laws to real world objects and make successful predictions. Newton's laws, rockets, everything. So then that in that sense, this definition is an accepted definition, and in that sense, it's a correct definition. And yeah, here what we did is we kept things simple. If you see, sometimes we can argue a lot just to just to show that we are knowledgeable or just for the sake of arguing, but it's no point. Now maybe this velocity example was not a very good example, but I think it somewhat it got the point across to you. The reason I'm saying is that even recently I did a project all by myself. Not the I also did a project in IMSC Chennai, but this is not that. I'm talking about a paper I wrote on my own. I think I mentioned this once or twice in my previous YouTube videos, one or two previous videos as well, that I tried to build a system of four coupled nonlinear differential equations, and using that system of equations, I tried to model how human relationships and human emotions evolve over time. But the problem was my model is limited to only two humans, so it's kind of limited right now. Even limited, even then it's very complex. So more complexity would be difficult to handle. And then if chaos sets in, if you have read chaos theory, then we cannot just keep on increasing the number of differential equations in a system, because after one point it will be unsolvable, like a three-body problem. It's no solution technically exists. You can analyze it to a little extent using computation and numerical methods, but yeah, solution in that sense not possible after a certain point. This is all in the domain of nonlinear dynamics. We are no longer talking about everything is like a fixed trajectory, everything. There is some plus even in my equations there is a random term, like apart from the parameters and the functions, the functional dependencies of the variables, apart from the parameters and the variables, there is a stochastic noise term. Right, so it's anyway random at every time step. If I start a numerical simulation in my model using the exact same initial conditions, I will within the limits I will get slightly different phase trajectories or slightly different plots outcomes. And yeah, because of the stochastic term, random term, at every time step it will draw randomly, it will draw a number to simulate real world noise. It will draw a number from within a range. So I've basically defined a normal distribution with zero mean, because I don't want any bias in my system, and some non-zero standard deviation. But a standard deviation should not be very large. I mean, the noise is just to introduce some realistic fluctuations. It cannot direct the behavior of the system. If it directs the behavior of the system, it's not technically noise. Then it's an important parameter which is directed. I mean, which is kind of definitive parameter. Noise means its effect should not be very strong, and it should be both ways. Otherwise, if it's in a single direction, it's a kind of predictable or at least a definitive force. It's not really random noise. So when doing this model, I understood when doing this work that initially I did a little mistake. I started with a lot of parameters, many variables, and just to model each and every. That's not possible technically, but to model as many as possible this complexities of human behavior, human emotions, you know. But then I understood that even though by this I can make a pretty good toy example, a toy model, mathematical toy model, but studying this model realistically, for that I would need access to real data of maybe some psychological studies, and then curve fitting or something. I would have to manually try different initial conditions and see if there is any value for which this my system is behaving strangely, which cannot be explained normally. And then I have to define, by that I can roughly define a range of the parameters. The parameters I've taken, I have explained why I have included them, their function in my model. But range, as of now, it's just a random number between 0 and 1. The emotions of the person is a random number between -1 and +1. -1 is very negative emotion, +1 is very positive emotion, 0 is neutral. But this is all just a toy, just a definition. It's kind of vague. We don't yet know exactly what is negative emotion, what is I mean, for a real human, what would we give the value of emotion? We have to arbitrarily pick a value. We were happy, let's say maybe +6. You're very happy, let's say plus 0.6. You're very happy, let's say plus 0.8. You are as happy as possible, let's say +1. But it's all vague. I think you can understand. It's a good model in the sense that it reproduces many complexities of dyadic human interactions, and it also I have done some analysis. It also works in many cases as long as it's between only two persons. Even I have simulated noise. I have taken into account third parties and everything, but they are not the main agent of the system. The main agents are just two agents. It's a dyadic system. Okay. So it's a good model because I think it's there are not many models like this. So it's a kind of first of a kind approach. At least I showed where I'm running into difficulties and the phase plots and everything. But again, it's a very vague, as I already told you. So then was kind of forced to keep things simple. So what I did was that I removed the noise initially. Since it's not a biased noise, I can just remove it and study the rest of the system, the deterministic system, very carefully. Because if you want to do fixed point analysis, suppose you have a parameter x and you have dx dt, the time evolution of x you want to study. So you write the time derivative dx dt equal to, you have some terms, so define a complex differential equation, non-linear differential. Maybe you define 2 or 3 more equations and maybe couple them, like let's say dx dt is the equation, and in that equation in the right hand side there is a term y, and then we have a equation dy dt which depends on x, so then it's a coupled system, right? Anyway, point is, then you can define the equation. So what I did was, I first of all I assumed the noise to be, I just forgot the noise term, and then I put dx dt. In my case the variable was not x, but just for giving an example, you put dx dt equal to 0. That means whatever was in the right hand side, you set that equal to 0, and then you can calculate, or maybe if not possible analytically, you can try to find out the fixed points. What are the fixed points of the system, right? Yeah, so that is the thing. Now you can find out the fixed points of the system. I'm sorry, I got a bit carried away. So then once you are done with the fixed point analysis, that will give you a very, yeah, even by looking at the phase trajectories, you can, or just plotting different variables against different variables, you can understand whether the system is drawn to some points, attractors or repellers or whatever. But to actually understand if it's really attractor, you need to find the, maybe you need to find Lyapunov exponent, you need to do the fixed point analysis, bifurcation analysis. This is, you have to do the mathematics, and that's possible only if your model is simple. I mean, start simple, study the model as much as possible, and then you make it more complex, to then you add noise or whatever else you want to make it realistic, right? That's the point. That's the example I wanted to give in like physics or academic point of view. But now even in general life, even if real life, this habit of complicating things, whether it's a, maybe between person, it's a relationship issue, reading too much into something which is actually meaningless. Maybe that person didn't reply to you soon because the person was outside or in a crowd or something, but you are like, oh, usually that person replies me quickly, but not now. That means maybe there is like, he has developed feelings for someone else other than me. I've just given an example. This kind of nonsense, I mean, that could be true, but then why are you like so bothered by this? Number one. Number two, one more example is that we always in our profession or academics, we always try to show a very inflated version of ourselves. Maybe the work I do is not really that interesting or not really that difficult, but when people ask me that, oh, what field do you work in, and if the people is not in my field, otherwise he can catch that I'm lying, they can catch that I'm lying, then I'm like, oh, the work I do is like very interesting, it's very difficult, as if that's, we all like to flaunt at times, right? Maybe I also do at times, but the complicating things just for the sake of looking cool or something, because maybe this is not like a big mistake. I mean, maybe we'll not have to not run into serious trouble for this, but trust me, we have enough complications in life, so we don't need any more add additional complications. Number one, I mean, this is the next example. The next is that, why should we keep things simple? Because this is a very logical point. So far the previous point was just from experience, okay, but this is a very logical point. If you start simple, if you study the simple things, it's possible to understand a simple thing, a simple object or simple phenomena, whatever, in all its aspects. Understand this logically. If I give a very simple thing to study, you can understand it in all its aspect very quickly, very easily. Now if I give a complex system, you cannot understand it. If it's very complex, maybe you cannot understand it at all. You can only analyze it and maybe find some patterns or something, but you cannot fully understand it. Or even if it's like maybe not so complex, but definitely a complex system, maybe you can understand parts of it, you can understand one aspect of it very, like fully you can understand one aspect of it, but even then understanding all the aspects of it is in most cases impossible, because a complex system means it has a lot of interacting parts. So which part affects which part in what way, all these things, right? And under what conditions. So, and more complex the system, this number of possibilities blow up, and after a point it's not really possible to analyze it at all. So that is the thing. Now, but the good thing about starting simple, or developing a solid foundation in simple systems before moving on to complex systems, is that if you start simple, you can at least understand the simple system in all its aspects. You have no loopholes, no, in your foundational level. Then you slowly move on to complex systems, slowly a bit more complex, then a little more complex. I'm not saying it will, of course there is no guarantee that you will understand the complex system fully if you understand the simple system, and you will not, in many cases you will not all systems can be studied, can be understood that way. But you will have developed better methodologies, right? Instead of studying complex systems from the beginning and forming a maybe a vague understanding. And that is what I wanted to discuss in this video. Keep things simple and always remember our limits. By that, I don't mean to demotivate you or challenge you. Yeah, it's a very it's very easy to say the sky is the limit, and it's not only easy to say. I think in some situations it's also good to think that way. We all know that in reality, sky is not the limit. We all have our limit. We will die after 80 days, no matter whatever we achieve within those 80 day. I mean 80 years. I'm sorry. On average, 75, 80 years, or even earlier if you're unlucky, or maybe I don't know. Anyway, but the point is, you should not like the point I want to the thing I want to tell you is that number one is keep things simple. Number two is you should always remember your limits. By that I don't mean that you should always demotivate yourself and say that, oh, since I come from a normal background, cannot do something extraordinary, I have to remain ordinary. That is not what I mean by sticking to your limits. I in that sense I never cared. I never stuck to my limits. I was not from a very like financially rich background. I am not right now, but that has not been an obstacle in any of my education, higher studies, any of my education, or even apart from education, like everything. I have been in that sense. I have always got what I wanted, even beyond the necessities. I must say, thanks to my father and mother and all my some of my other relatives as well. But some of my other relatives in the sense mentally, and also in my college when I was right now I'm about to start my masters. That's different. But when I was in India in my from my undergraduate in my bachelor's, I stayed in my uncle's house. So I could have afforded a hostel, but I had some psychological. I mean, I was not ready to share room with an unknown, like a student at that point of time, because I was very attached with my parents and I had to call my parents every night and talk with them, video call with them for hours. And of course, if I have a roommate and if I keep on chatting 3 a.m. in the night, that will be problematic for both of us, especially for the roommate, because yeah, I mean, basically I was not accustomed to staying alone, and especially that hostel life. That's why. So my relative, so money was not a problem, but still, if my uncle had not allowed me to stay at his place for the 3 years of my undergraduate, things might have been a bit more difficult for me. So in that sense, so yeah, the point is, what I understood is that what I understood for the last few years of my life. It's how should I put it? It's always a good idea to remember about your mortality, but that doesn't mean that, okay, I am mortal, I'm not immortal, I will die after a few years. So why bother about studying? Why bother about doing something new? Why bother about going through all this hard work and effort? No, that's not the thing. I mean, if thinking about your mortality brings these things to your mind, then you better don't think, because I'm not sure if my whatever I'm going to say, if this would work for everyone. But for me, it works. That's why I'm just sharing this with you. Whether it works for you or not, you have to find it out. If it doesn't, then best not follow this. But for me, it's good to stick to our limits. In the sense, it's always good to remember that we are here for a finite amount of time. So even if everything is not perfect, instead of complaining and making things complicated, it's better to just enjoy life and at the same time do some hard work, but not because you have to do it, not because you have to get some grade in exam. All of these things are important. There is some constraints put on us by society. If I say that I will just do physics but I don't care about any funding or anything, the money will not come flying to me. But even within all those limits, let's try to be like, try to be do something as meaningful as possible. Now meaning can vary from person to person. I'm not saying you have to do physics, but this attitude, and to do that, first and foremost, you need to keep things simple, both personally, in your personal life, in your relationships, in your professional life, in your work, everything. Yes, you need not chase simple things. You can always and you should always aim to understand interesting phenomena which are usually complex, but your approach should be not unnecessarily complicated. That's what I mean. And whenever I think that I'm mortal, that also gives me some urge to do something meaningful, because oh my god, I'm here for a few years, I should do something meaningful. Why? I know I will be forgotten one day. After I die, maybe for a few years, my friends will remember me. After that, maybe they will also. And anyway, one day the entire human race will be wiped up. So all of these works which I'm doing, none of this is permanent, and I very well know that. But still, whenever I think about that, I will die after a few years, not like maybe after 60 years, which is not really few years in human standards. But yeah, in the in the grand scheme of things, 60 years is just like 60 seconds, or maybe even less. So whenever I think that, I feel more motivated to do something meaningful, instead of getting like demotivated or something. So if it's the same for you, you can go ahead, otherwise not. So keep things simple. That's what I mean. Keep things simple and always know your limits. Know your limits is one more interesting aspect to this advice, that stick to your limits. One is I told you about mortality and stuff. The second one, and this is especially relevant to you if you work in science, if you're a researcher in science. Second is that we should always remember that everything in science, almost everything in science, from the foundational level, it's kind of after a certain point, it rests on assumptions. Now that is not necessarily a bad thing, because after all, this is the only way we could have built physics or built a science to explain the world, because this is not mathematics with the axiomatic approach will, I mean, these are assumptions, fine. Like I told you, velocity, it's also the exactly, you cannot derive that velocity is distance over time. It's somewhat of an assumption if you think about it, but it's a good assumption because it works, and using this formula we have been able to do a lot. So it's a correct assumption for all our purposes. It's a correct assumption. Right. Now the point is we should remember this, that this is all assumption. At some point, if you go down deep down, like let's say you start with a very superficial level question, why does this happen? Science gives you a very satisfactory answer. Then you go deeper. Okay, now we understand this happens because of this thing. So why does this thing happen? And as you keep on doing this, after a point you will find that if you just keep on doing this, you will yourself understand that actually we don't know the exact reason deep down. We have assumed it that way, and it more or less matches with our experience, our expectations, our observations, and we have a very like theory which fits in with the other pieces, and then that's why it's seen to be the correct approach. And then that's that. You don't know anything else about it, but it's correct. Now I'm not saying discard these ideas, of course not, but it's still good to remember at the back of your mind that uh, because sometimes when we're doing science and when we learn things, or even when we develop new theories, new formulas, we unconsciously start believing that these are universal truths, but that's not the case. So if you always keep this habit of sticking to your limits and reminding yourself that everything is after a point assumption, then if something else comes up in the future which is in contradiction with your theory, it will be easier for you to accept it, because usually humans will unconsciously form bias to their theory. So even if your theory is actually wrong, if you come to know that, then you will try to maybe unconsciously in many cases you will try to protect your theory, but that is in that sense that is not really contributing to the progress of science. That can slow things down. So you should always be unbiased. A true scientist should only care about real progress, finding out new stuff, not about okay, my theory is correct and his theory is false, then I'm successful. No, that is not, that mentality is not right. Even though it's easier said than done, because in today to survive in academia, not succeed, even to survive in academia, you need to have a lot of publications, a lot of back end stuff is going on, all this I don't know, like a lot of unethical practices are going on in academic publishing, and you need to after some certain point you need to comply to them, otherwise your career is gone technically. Very sounds very harsh, but it's the truth. I mean, not only in India, even here. I mean, not specifically in the European Union, even in US. I think this is a problem all over the world. Of course, at least in these countries, we get enough funding. People get enough funding, and in general the professors are also much more supportive. But this is no paradise better than India in many respects and in general. But no, for academia you have it's a long battle, and if it was a battle, if it was just an intellectual battle, just a battle with ideas, I would have loved that. I mean, that's why people come to academia. The ones who come to academia, they do because they love thinking and these intellectual battles. But unfortunately, to survive in academia today, you have to fight a lot of other unnecessary battles created by the system. You have to, wherever you are, there is no like no other way. So anyway, these are the few things I wanted to discuss. Very again, sorry for this. I was just again a very unscripted, unplanned, quick video. But anyway, thank you.